Okay, so welcome everybody to today's session of the Newton 1665 seminar series. And the first speaker today is going to be Anupam Mazumdar, that he's going to discuss about a recent proposal to test the quantum nature of gravity. So please, Anupam, start your sharing. And yes, stage is yours, please.
Okay, thanks. Thank you very much. So thanks, Daniela, for this kind invitation. And it's really a privilege to talk about something which we are really very excited about. And it's about quantum gravity witness via entanglement of masses. So we call it a QGEM protocol. And so this is the work which we have done with my close collaborator, Bose, who is actually present in our audience. And the work appeared in 2017, and then we made gradually small progresses. And simultaneously, there was another paper from Oxford group by Marletto and Wedrell, which appeared almost on the same day. So the idea is that how you're going to test quantum aspects of gravity. So that's the question which we are asking, and that's the question we want to understand. And as I said, that we are quite lucky to have excellent collaborators. They're all coming from quantum information, quantum technology, from the gravity side. So it's a kind of like bringing people, all the frontiers from all together under one umbrella. So as you can see that when we had this paper, I mean, there were quite a lot of excitement in the community. And perhaps this is perhaps one place where if we want to really understand the quantum nature of gravity, we really need to understand the quantum information, quantum technologies. So this is, it's really an interesting avenue if you really want to make some groundbreaking contributions. And you will see that there are plenty of challenges. We're talking about the challenges, enormous challenges, which we do not have the technology right now. Nevertheless, I think this is really a dream job for any young person and for any of us. Okay, so the question is very simple. Is gravity classical or quantum? And how am I going to test it? A very simple question. It has been lying there for almost 400 years. I mean, of course, at the time of Newton, perhaps we didn't know about the quantum mechanics. But nevertheless, I mean, in the past 100 years, we have been asking this question. We have been chasing our dream. Very simple question, but it's extremely, extremely hard to understand. Where lies the boundary? And the boundary lies actually, unfortunately, in the case of gravity, or fortunately, we know that there exists a Schwarzschild radius. So the cuteness of a cat, if you really want to, if you're looking for the gravity's Cheshire Cat, now that cat, how big the cat is, how macroscopic the cat is, that and how cute the quantumness of the cat is, that depends how close you can perform the experiment close to the Schwarzschild radius. Now, as you see that if the cat gets bigger and bigger, macroscopic system, it gets uglier and uglier. The quantum feature, extracting the quantum feature becomes harder and harder for us. And not only this, it actually, since the entire discussion, the forum is based on 1665 Newton's formulation of universal laws of gravitation. So it's also a tussle. Now, for the first time, we are asking ourselves that what is exactly this origin of Newton's gravity? And so it's a tussle between the old formulation, 400-year-old formulation of theory of gravitation with respect to the new approach of quantum mechanics or quantum field theory, where we want to understand the basic origin, how the force appears in nature. So today's science fiction, whatever we are talking about is really a kind of science fiction, but tomorrow is reality. Now, you can ask various kind of questions. Now, you can ask, can you take a graviton and put it in a quantum superposition in a laboratory? The answer is no. It's extremely hard. Can you mimic like coalescing black hole in a laboratory? Take coalescing atoms and study the loss of gravitons. And again, the answer is no. You can do the back of the envelope calculation, and you will find that number of gravitons you would emit is so small that it would be very. Last but not least, and the simplest question perhaps you can ask, and perhaps there is an answer for that, is that can you really witness the quantum entanglement due to quantum nature of gravity? And the answer is yes. And as I said, that I have had a very strong collaboration and huge collaboration with Sogato Bose, with whom I have been discussing for almost years now. Almost 10 years we have been thinking about this problem, how to really, test this fundamental question. And so I've had a pleasure of discussing with many people, Jan Yambyon, Ashtaker, Abhay Ashtaker, experimentalists, leading experimentalists in the field, Marcus Aspelmeyer, Marcus Arndt, Frolov, Roger Penrose, Carlo Rovelli, Sain, Veneziano, and many other stalwarts of the present day theorists. So this is the question, the last piece of question, that can you really witness the quantum entanglement? This is what I'm going to now focus for the rest of my talk. So what exactly is all about? So this is the quantum gravity witness. So the question first will be, how do you create a witness? How do you read the witness? And what are the associated challenges? What are the challenges that we need to overcome in order to read those witness, prepare the witness? And towards the end, if I get some time, then I'll just mention a little bit about the quantum gravity. But for the most of my time, I'll be talking about the experimental setup and the logic behind how to test this quantumness of gravity. Now, one thing which perhaps has bothered all of you in the community, it's not the first time I'm asking these questions. Many, many people have asked this question. How do I constrain even the Newton's 1/r potential at very, very small distances? And this is the paper coming from the Adelberger's group. It's a very new paper, 2020 paper in the month of February. And you can see that the experimentalists, what they like to do is that they like to plot the Yukawa kind of correction on top of the Newton's potential. On y-axis, you have alpha, and on your x-axis, you have got lambda. And you see that the current experimental tests are the exclusion zones. The yellow region is the exclusion zone. And you can see that for very large values of alpha, we have fairly good constraint. But when it comes to very, very small values of alpha, very close to the Newton's potential, just 1/r potential, there's hardly any constraint. And the best constraints coming from the Adelberger's group is this blue line, vertical line, which comes down roughly 3.8 times 10⁻⁵ meter. And if you convert that into some energy scale in natural units, you find something like 0.002 electron volt to the power 4. And as you can see, that there's a huge gap. Now, all the way from 0.002 electron volt to the power 4, all the way to the Planckian energy density, we are assuming that Einstein's theory or Newton's laws would be valid. But there is no direct evidence of that. Now, of course, like LHC puts in direct constraint, the fact that we have not seen any Kaluza-Klein modes. Now that constraint comes around roughly 8 to 10 TeV, which is roughly 10⁻⁻17 centimeters or so. But keep in mind, that's an indirect test. So I believe that, and many people believe in our community, that perhaps there's new effects hiding when it comes to gravity. And the scale could be anywhere, anyone's guess, as long as we don't see it. So having said so, many people have thought about how to test, how to play with quantum mechanics and gravity. It's a topic which is not new. It's not the first time I'm discussing this topic. The first time perhaps it was discussed in the experimental context was Cow experiment by Colella, Oberhauser, and Werner's experiment. And this is a famous experiment. You can open Sakurai's book and you will find maybe 5th chapter, this famous, the discussion of the famous experiment. So people have measured given the gravitational potential, classical potential, people have measured the various energy levels. So in the case of Cow, it's a cold neutron, and a similar experiment was performed in Grenoble way back in 2000, where they've taken the cold neutron and they have bounced it and they have measured the various energy states. Now you can ask, well, gravity is extremely, extremely weak. Well, how come we can see we are sensitive to this quantum phase? And the reason is that in the quantum phase, what appears is the Newton's constant in the numerator and h bar in the denominator. G is a tiny number, h bar is a tiny number, but the ratio need not be. And that's the part which you can extract. So there is a sweet spot where you can, if you can tap in that sweet spot, you may be able to find some interesting effect. And precisely this effect we have actually tapped in order to construct very recently atomic interferometer, roughly a meter-sized interferometer, which can even detect gravitational waves. And if time permits, I will talk a little bit about that. It will be a sub-hertz detection of gravitational wave interferometer. It's not like LIGO or LISA, but nevertheless, it's a very tiny detector where you can place anywhere on Earth. Good. So the serious attempt when it comes to quantumness of gravity, the serious attempt was made by these two gentlemen, Don Page and Gilker, way back in the 80s. Now, the idea was very simple. So they wanted to falsify the semi-classical nature of gravity. So by semi-classical, what I mean here is that the energy momentum tensor, you treat it like quantum, but the G mu, the Einstein's tensor, you treat it classically. Now, if the T mu, if the matter component is really quantum, then you can create a macroscopic superposition. So and once you observe the system, either the system will be here or here. It's like a Schrödinger's cat. Now, based on this, they were able to kind of falsify, if not falsify, they were able to make a statement that this semi-classical treatment of gravity is perhaps not feasible, it's inconsistent, but they could not really falsify, or they could not really, brought the argument that gravity ought to be quantum. Now, that statement was still lacking in this paper. So it took something like 20, 30 years to bring that statement, something like exactly like Bell's inequality, how you're going to test it with a very, very sharp kind of argument. Now, way back in 2013, 2014, we had an amazing time when we came to know that BICEP might have seen this primordial gravitational waves. Unfortunately, it turned out to be that it was not the primordial gravitational waves. That's a different story altogether. But simultaneously, at the same time, people thought, hey, if I could see these primordial gravitational waves, does it mean that I have seen quantum aspects of gravity in the sky? We have to be a bit cautious here. The answer is yes, of course. Even I would love to see that, this effect, the quantumness of gravity is present in your sky, but one has to be a bit more cautious. The reason is if someone is die-hard classical mechanics guy, doesn't believe in quantum mechanics at all, or quantum gravity at all, maybe quantum mechanics you believe, but not quantum gravity, then you can always come up with a very crooked initial condition, which can match exactly the tensor perturbations, which would be given exactly by your quantum initial conditions. So just the presence of mere H bar does not suffice. You have to work out a little bit more, to dig out a little bit more to say that, hey, look, this is really quantum gravity. So, so what exactly we are after? We are after a very sharp, razor sharp kind of argument. So you create a witness, and it should be such that if the witness is positive or negative, depending on how you choose the witness, then you can conclude that gravity is quantum. And if you don't see that, then there is no way you can conclude the nature of gravity. So that's the kind of razor sharp argument, razor sharp witness you have to construct, because the topic itself is very, very sensitive. So what are the key ingredients you would need in order to falsify this? So what you need is this, one of the important ingredient is this macroscopic superposition. And people have created macroscopic superposition with various range of masses. Of course, right now the best laboratory constraint comes from the Vienna group. For Marcus Arndt's group, they have taken 10⁻⁻21 kilograms, and they have created a macroscopic superposition. It's like Schrödinger cat state. The other feature, which you cannot find in any classical mechanics or any classical system, is the quantum entanglement. So you see, inherently the vacuum is highly entangled. The reason is you can create Schrödinger pair production, electron and positron. Now, electron and positron, they are entangled. You cannot separate them out. So that's the classic example of your Bell's pair. So another critical ingredient is you have to see the correlation, quantum correlation, where you can distinguish from classical correlation with respect to quantum correlation. And this quantum correlation comes essentially from the entanglement. So these are the two ingredients which goes into this argument. And the third, but last and not least, is very powerful theorem, which was known to quantum information. And actually, it was not known to me personally. And it was enlightened to me by my colleague, my friend, Bose, who actually told me. And once he recited this theorem, it became quite clear where we are running after. And the theorem states, it has been proven very mathematically with the help of majorization and all sorts of techniques. We are not going to go into that. I'm going to give you a very simple example. Suppose you're sitting at CERN, you have got a coin, and imagine that coin has a Hilbert space. You have heads and tails, And I'm sitting in Groningen, and I've got a coin which is a quantum coin. It has a Hilbert space up and down, heads and tails. Now I toss the coin billion times, you toss the coin at your end billion times. But as long as we are establishing a classical connection, classical communication, I'm not going to influence your outcome. You're not going to influence my outcome. It will always be 50-50. In order to change this ratio of 50-50, if you want to make it 51 and 49 or 51 point something and 48 point something, I need a quantum communication. So this is what LOCC tells us: local operation and classical communication. So at your end, if you have a quantum system, you have a quantum operation going on locally. But at my end, there's a quantum experiment I'm running with a very local operation. I'm setting up, like unitary operation is a simple example of that. No way I can really entangle you and me as long as we are far away. So what you need to do is that you need to create something different. So what you need to create is local operation and quantum communication. And this is what will be very, very crucial for the experiment as well, as you will see soon. So let's go back to this question of what is the origin of the potential? So in principle, if someone is very diehard classical mechanics, and he would say, look, gravitational potential is given to me, Coulomb potential is given to me. Once you accept that, you don't ask the question, what exactly gives rise to that potential? So you can ask the question in quantum mechanics or in quantum field theory, what gives rise to the potential? And it's the same famous experiment done by Chadwick. He took the gold foil, he bombarded the alpha particle. He wanted to understand the Coulomb potential of nucleus, Coulomb potential. So in a fixed potential, in a fixed target, he was doing the scattering problem. So that's pretty much like a given classical potential. You want to understand initial and final state. But we know that in a transition matrix, if I go to the first order in perturbation, I have a completely new term which appears where I sum over all possible intermediate state. That gives you the concept that there is a mediator. So the force now is not instantaneous action or instant action at a distance, but it becomes force arises because of exchange of some quanta. And when you take the time order diagrams, what you find is nothing but your Feynman propagator. So this is something of very simple, very rudimentary physics, which all of us know in this forum. It's nothing very fantastically new or challenging for any of us. So now we know that, yes, in quantum mechanics or in quantum field theory as well, I mean, we can generate a potential. Essentially, it's nothing but the mediation through the mediator. So the Coulomb potential, say in the case of electron, positron, the Bhabha scattering or molar scattering, you take the non-relativistic limit, you get the Coulomb potential. The photon, off-shell photon is your mediator. In the case of gravity, of course, is the same. You have a graviton which mediates, which is the off-shell graviton, which mediates your force between you and me. So the off-shellness of the particle is actually a non-classical feature. And here comes your local operation and quantum communication. So first of all, the off-shell quanta doesn't have the classical equations of motion. It has a non-classicality built in. Now, non-classicality doesn't mean that it has to be quantum mechanics, but you can ask yourself, how many systems do we have which have this kind of feature? And the other important ingredient is the non-commuting operator. Both of them are present in your off-shell picture. And so essentially, we know now we can compute in the Einstein's gravity around Minkowski background. We can find the graviton propagator, the spin 2 and spin 0 component which propagates. You take the 2 energy momentum tensor, the conserved energy momentum tensor, you sandwich the propagator, you get the Newton's 1 over R potential. So it's a very simple arithmetic. Now, here then you can ask is that what are you going to do with the experiment? What the experiment is going to distinguish? So you have, on one hand, you have got a classical scattering, the scattering with the classical potential, initial state to final state. You have a quantum picture. We have the second order perturbation theory where we have brought in the concept of a propagator. And of course, as a theorist, you would like to see, hey, can I go beyond this? Can I really probe the loop effects or not? And that's, again, extremely, extremely interesting. And there is a possibility. Suppose you take two cosmic strings, two infinite cosmic strings in 3+1 dimensions. At the tree level, they do not exert any force. There's no potential between them. because you can see it's very easy to understand. You take a sheet of paper, you cut a triangle, essentially that's your you create a defect angle, you lift it, that's your cosmic strings. But the sheet of paper has no curvature in 3+1 dimensions. So two cosmic strings, they do not exert force at the tree level, but the force arises, the potential arises at one loop level. But the problem there is that the effect becomes G square. The phase, the quantum phase, in the classical case is G over h bar. In the quantum case is just the tree level graviton exchange will be G over h bar. But at one loop, it becomes G square, and G square is a very, very tiny effect to be detected. So it's extremely challenging, but nevertheless, who knows, in future, maybe the technology will be available for us to even see the one loop effect of graviton exchange. So just to keep a perspective, photoelectric effect was known almost 100 years ago. It took almost like 80, 90 years to create superposition of photons. Now it is a kind of like a regular experimental game in many of these experimental labs. So this is the picture on the right-hand side taken from Gerhard Rempe's group of Max Planck Institute of Quantum Optics. Now you can play many, many games. You can put the photon in various different quantum superposition of wavelength, frequency, polarizations. You can do many things. So this is just to give you a hint that these experiments are extremely, extremely sophisticated and extremely, extremely challenging. In the case of photon, it took 80 years. And maybe in the case of graviton, maybe it would take another 20 to 30 years. But this is the place where no one has ever gone before. So this is the frontier we are opening now that perhaps needs huge amount of devotion and huge amount of challenges to be overcome. So what is the QGEM protocol? So quantum gravity induced entanglement of masses. The protocol is exactly the same as I explained to you. You have got two interferometer. This is a quantum system, Alice's interferometer and Bob's interferometer, and you're tossing the coin. And at the end of the day, you want to see how many times you have got heads and tails. So you build a correlation. So in order to build a correlation, what you need is that you need to embed spin inside the system. And technologically, it is possible, it is viable. You take a diamond has an NV center and nitrogen valence bond where you can attach a spin. So the experimentalists can attach a spin inside your diamond, and that becomes your ruler. And you let it fall through the Stern-Gerlach kind of experiment. And so the presence of inhomogeneous magnetic field, the spin essentially will give you the Stern-Gerlach effect. And at the end of the day, if you can close the loop, then you will be able to measure the correlations. So this is what essentially the experimental setup is all about. Now, in principle, as I said, that what is important is that so if the graviton, if the two system of Alice and Bob, if they're interacting via graviton, off-shell graviton, they are going to get entangled. And you can measure the entanglement phase, and you can measure that with the help of this spin correlation. So how many times you have got spin up and spin down, you can look into this pattern, you can look into the correlation, and you can establish whether gravity is classical or quantum. And you see that in the entanglement phase, what appears is the ratio delta phi, which I have mentioned here. What appears is the G over h bar and the masses and the nearest distance d minus delta x. Now, if you want to get the order 1 effect, you need the masses to be roughly 10 raised to minus 14 kilograms. And you can see that roughly 7 orders of magnitude you need to overcome. From 10 raised to minus 21 kilogram, which has been done in Vienna, now you have to go from almost 7 orders of magnitude. The closest separation distance has to be roughly 200 micron, and the superposition delta x separation should be, the splitting should be roughly 100 microns. And you can construct a witness, and this witness is exactly the Bell's witness. And in this particular witness, because it's a basis dependent, so if the W is greater than 1, you can establish that the two system, Alice's and Bob's interferometer, now have now got entangled. And if there are no other interactions, and if the gravity is the sole interaction, you can establish that the graviton is really quantum in nature. So that's the experiment. But now how you are going to ensure that the only interaction is the graviton? There's no other interaction. So this is the challenge which we have to overcome. So we have to overcome all the electromagnetic interactions, including the Casimir interactions, because after all, we are playing with diamond. Diamond has a dielectric properties that will lead to Casimir interaction. And it turns out for these parameters which I have mentioned here, the gravitational potential wins over the Casimir potential. So the entanglement phase due to gravity is 10 times bigger than the Casimir entanglement due to Casimir interaction. So you can build up different bases as well. And if you're not happy with the basis dependent witness, you can go for essentially entanglement entropy, von Neumann's entanglement entropy. You compute all possible correlations and you construct the reduced density matrix. And from the reduced density matrix, you compute the entanglement entropy, which has to increase always. But as I said, there are plenty of challenges. You have to, in order to perform this experiment, you know the density of diamond, you have to know the property of a diamond, you have to cool the diamond from inside because there are phonon interaction which can destroy the correlation of the spin coherence. You have to put the entire thing in a chamber with a temperature roughly around 1 Kelvin. You have to have the perfect vacuum, the kind of vacuum which actually CERN uses, one of the best vacuum where you have to go for 10⁻⁻15, 10⁻⁻16 Pascal. CERN has even better record. It goes to 10⁻⁻18 Pascal actually. So you need all these kind of things in order to even avoid any collisional decoherence. So that if a particle comes in, hits the diamond, it will actually destroy the coherence. If a photon comes in and hits the diamond, it will destroy the coherence of your spin. So it will destroy this superposition. And of course, there are other ways you can destroy the superposition. If you imagine this year's Nobel Prize winning candidate Penrose, if Penrose has this Penrose's way of collapsing the wave function, even that will also lead to destroy the coherence of the system, destroy the superposition. So you see that now you're probing physics, the fundamental physics, even the foundations of quantum mechanics, even foundations of gravity. So this is the place, is a frontier where you're mixing many, many different things. And of course, as by no means is easy, there are many, many challenges. You can overcome some of the challenges by putting a Casimir kind of like Faraday cage. You can take a conducting plate and you can separate the two systems. So the two systems will not feel any Casimir interaction, but the Casimir interaction will be felt by the one system and the conducting plate. So there are ways you can ameliorate the system, ameliorate the parameters of the game. And so you can bring the now macroscopic superposition, the masses of the system to be not from, 10⁻⁻14 kilogram, which is very, very daunting. You can bring it 1 or 2 orders of magnitude smaller, 10⁻⁻16 kilogram. You can bring it down to 10⁻⁻16, which is kind of like feasible. 10⁻⁻17, 10⁻⁻16 is the game which people are now playing. And hopefully within, say, 10 years time, maybe this kind of macroscopic system can be placed in the superposition. So there are ways you can actually ameliorate the system, ameliorate the parameter space by putting the Casimir or the Faraday cage, as I mentioned. There are ways, also you have to pay attention that there should not be any source of decoherence. So decoherence is the main thing which can actually destroy the coherence of your system, the superposition. And we have, I think, so this is a plot where we have the dotted line for interaction time scale of 1 second. The pressure is around 10⁻⁻15 Pascal. So you have to have your phase, the entanglement phase has to be larger than your decoherence scale. So the decoherence scale has to be below this dotted line, the horizontal line. So black body radiation, the cooling, the heating, everything can destroy the superposition. You can also think about even the gravitons can hit and destroy the coherence. But it turns out that it is the graviton, essentially the gravitational waves are very, very weakly interacting because graviton couples very weakly. So this decoherence or the dephasing is extremely, extremely small. One of the things which we have learned, and I think one of my colleagues is present, Marco Torres, he has contributed quite a lot in this. So you can ask the question, where would you like to perform the experiment? Even a butterfly passing by me will actually lead to dephase my system. So that itself places a huge bound on the exclusion zone. So you have to perform the experiment and you have to have something, say, let's say a couple of 100 or 5 or 10 meters away, there should not be anything. So you have to place the system in a place where you can get rid of any jitters, any relative acceleration, any finite size box effects, and so on and so forth. So the best way to perform the experiment, I will not go into the details, but the best way to perform the experiment will be to have a drop tower. Now in Bremen, we have a drop tower, but the drop tower, the exclusion zone of drop tower is not sufficiently large. So in a Bremen's drop tower, you can perform this kind of experiment. suppose you move, all of a sudden there is a jerk. If you perform the experiment in Geneva, the Lake Geneva's up and down movement during the winter or any seasonal changes will all destroy essentially your coherence of your system. So all these things you have to take into account. This is the kind of computation which was performed by Kip Thorne for his LIGO. And so some of the things, technology, we are now borrowing it from LIGO. And what it turns out, so this is just a very, just a sketch. You really have to perform this kind of experiment under the ground. You have to create a drop tower under the ground. You have to have an exclusion zone of 5 to 10 meters. And you have to drop it for roughly 50 to 100 meters, because you go down because the seismic noise is very low. So some of these things you have to now really get into all the nitty-gritty details. One of the biggest challenge, of course, is how do you create a macroscopic superposition with a very, very heavy system? That itself poses a very tremendous challenge. We really don't have the technology even to do this kind of, create large macroscopic superposition. So this is one frontier where a huge amount of effort will be theoretical effort in engineering. The macroscopic superposition will go in. It's almost like LHC. You want to accelerate your particle in the process of creating your Stern-Gerlach. You have to accelerate it so fast that you can create the superposition, maintain the superposition for sufficiently enough long time, and close the loop. So this requires a huge amount of even designing, how to design the kind of experiment, what kind of material you would choose, and all the nitty-gritty details of condensed matter gets into the game. So since my time is running out, so few words. So there are a very interesting theoretical aspect. What it tells you, if gravity is inherently quantum, then we know that since matter is quantum, I'm made up of quantum matter. Daniela is made of quantum matter. We are all entangled universally through graviton. So this infrared effect of quantum gravity is the frontier which we can actually probe, which we can, do some experiment. With extreme UV, we cannot probe. We don't know whether string theory is correct or whether loop quantum gravity is correct. We may never be able to go into that regime, but the infrared aspect of quantum gravity, we can definitely probe in near future. Let's say 20, 30 years from now, we will have this kind of experiment. So let me, since my time is really running out, so I'll just say that this one experiment, simple protocol, actually unites all wakes of physics. You can talk about material science, cooling, refrigeration techniques, the quantum vacuum, Casimir patch potential. You have to levitate the system. You have to let it free fall. You can even probe beyond the standard model physics. You can probe the foundations of quantum field theory. You can probe even the light cone structure, to what extent the light cone structure is preserved. So you can probe the quantum version of equivalence principle. You can probe foundations of quantum mechanics and gravity itself. And beyond this, you can also probe even hidden sector physics. If you take instead of taking neutral masses, if you take charged particle, so they are interacting now, they are getting entangled by a photon, QED essentially. So you can do an experiment with the low energy frontier of QED. You can probe if the photon is coupled to axions or hidden sector axion light particle or hidden sector photon, then your entanglement phase will be sensitive to this one loop effect. So all these things, so one protocol can unite many, many different wakes of physics. So let me conclude here with the future outlook that I personally believe that testing quantum gravity is now really the final, perhaps the final frontier in theoretical physics. We have conquered many things. Of course, there are many, many theoretical challenges which we don't understand about even standard model physics. But in the case of gravity, perhaps this is the last holy grail which we need to understand experimentally. And we have a protocol. It's exactly like a Bell's equivalence of gravitational for the case of quantumness of gravity. So we have the protocol. Now it's a matter of technology. How much can we improve? And it's a matter of funding. How much can we do in near 5 to 10 years time and perform this kind of experiment and make it a reality? So with this, let me thank all of you for your kind attention, and thank you very much.
Thank you, Anupam. Nice talk. Are there any questions? If so, you can just speak up or raise your hand or anything.
Can I ask a question?
Go for it, please.
Okay. So on the theory part, I just want to ask, but assuming that the standard model is quantum and gravity is not quantum, is it consistent? I mean,
sorry, Michele, could you?
I'm asking whether, like, this proposal of gravity being classical, while the rest is quantum. I wonder if it's really consistent with unitarity, and by this I mean unitarity of the standard model itself.
I mean,
because normally when you take a theory, okay, and you throw away loops of some kind, this is inconsistent with unitarity. Okay.
I mean, I would say that you don't have to have it. You have to believe in quantumness of gravity before even talking about the loops. You see?
No, but normally in a theory, okay, so if you see some interaction, okay, it's not that you can ask yourself in QED, can I decide not to do loops, for example? Okay.
No, I can say
that's inconsistent with unitarity. Okay.
I mean,
since we measure actually the three-level coupling of graviton to matter.
Where do the question is where is it?
But on the other hand, you're saying, well, I didn't really measure the quantum effect of gravity. Yeah. I'm wondering if really removing that class of diagram is consistent with unitarity of the standard model, okay, not of gravity. Gravity will not be quantum, I understand.
So I think it's a good question from theory side. Of course, it is inconsistent, but the question remains that if someone is agnostic, you have to, when you have this kind of like argument, the question is, someone is diehard believer in classical mechanics. Of course, even I'm not a diehard believer, but I have to convince them. Mm-hmm. So the question is, how would you convince it? You need an experiment.
No, but this is a different question. But I'm just saying that if you discover that gravity is not quantum, okay, you're also discovering that the rest is not quantum in the sense it violates at some level of unitarity.
That's true. No, from theoretical perspective, we're all sympathetic about this point which you are mentioning.
Okay,
and not establishing it, and not only the establishment. It's just for the first time we will be able to kind of verify the off-shellness of graviton in a laboratory.
This I appreciate. Okay, but I mean, off-shellness of the graviton, I think I mean, even the motional planet is off-shell from that point.
Of course, everything is off-shell. In the quantum world, everything is off-shell.
Okay. No, I understand the difference between a theory argument and experimental arguments, but I'm wondering about the implications. Anyway.
Anupam, I would rather say, correct me if I'm wrong, that what you're actually testing is the ability of gravity to see superpositions as such and not as an average, which is, strictly speaking, is not even an off-shellness of gravity. It's just the fact that the graviton can exist in a joint system, a joint quantum system involving a graviton can exist in a superposition of state.
Absolutely.
Is this correct? Okay.
Absolutely, because you have got a superposition of masses. And
exactly. Okay.
Of course, the superposition of curvature is also involved in.
Okay, and there is a question in the chat by Roberto Franceschini that I can read, or if Roberto wants to speak, can speak. Since I don't see him speaking, I will read it. So he doesn't have the mic, that's why. So I'll read it for everybody. So is there been already something like a demonstrator in which the entanglement is given by much stronger forces like QED? So if there is an experiment.
So yeah, that's a very good question. Actually, I mean, people have done with the nanometer scale separation splitting. So at a very, very tiny scale, people have done this kind of experiment. They have not seen any, I mean, they have not measured the entanglement features as such, but the kind of experiment which we have in the case of ions, people have done it already, but on very small scale. So, but this is one of the challenges for us also. In fact, one of the experiments which perhaps one can do, and here the CERN will be extremely, extremely helpful, because you see Alice, in the Alice experiment, we have a heavy ions. Now, if you can take these heavy ions and suppose you can create the Stern-Gerlach kind of apparatus, let it go through a Stern-Gerlach apparatus, you can actually see this QED effect. And that would be wonderful if one can do this experiment. And, so it's now it's a matter of technology and how do you, tap this heavy ions, bring it closer to your chip, you kind of like, create a macroscopic superposition and see the effects of Coulomb low energy QED effects. And that would be wonderful if one can do that experiment.
More questions? I don't hear, not read anything. So I think we can thank Anupam again and pass to the next talk. So please.